So let's look at an example of the reactivity of these conjugated systems. How does that change what we know about how alkenes already react? The simplest possible example is just a conjugated system that is only a double bond or only two double bonds connected by a single bond like this. Let's react it with HBr. This is a reaction that we all know pretty well. Right? The double bond comes and gets the H plus. We break off the bromine and we end up with a carbocation. So we have all seen this before. We know kind of what happens next because we talked about it in the previous slide. This is going to have a resonance structure, and so we're not going to have the cation in just one place, right? The resonance distributes that positive charge between carbon 2 and carbon 4. So notice that we've added the hydrogen, so we add hydrogen to carbon 1, and now we have a cation at carbon 2 and carbon 4. And we also have Br minus around. And so now the question is, where is Br minus going to go? And the answer is it goes to both positions. So the bromine can add to carbon 2. We get a product that looks like this. Right, so the hydrogen adds to, or the hydrogen has been added to this carbon. We have a methyl group now. We get whatever this is, 3-bromo-1-butene as our product here. Or the bromine can add to carbon 4 over here, and we can get something else. So this is CH3, our double bond is here. We have a bromine here. This would be 1-bromo-2-butene. So we get two different products depending on where we add the bromine, right? And so we add the hydrogen to carbon 1, and then we have a choice. We can add the bromine to carbon 2. This is called 1,2 addition, right? So if we add the hydrogen to carbon 1, we add the bromine to carbon 2, we get this compound. Or we can add the bromine to carbon 4. This is 1,4 addition, right? Because we're adding our atoms to carbon 1 and carbon 4. So 1,2 addition will lead to the 3-bromo-1-butene here. This is 1,2 addition. Or 1,4 addition is down here. That leads to this one here. So the difference between these is, do we attack the carbocation that has not moved due to resonance, or do we attack the carbocation that has moved to resonance? Now, of course, both of these cations exist because that's how resonance works. It's just a question of which carbon does the bromine add to. We can get two different products. So anytime we get two different products, we want to know, can we pick which product we get? How do we know which one is correct for whatever our reaction is? If we want to make 3-bromo-1-butene, can we specifically do 1,2 addition in place of 1,4 addition? And so we want to look at these two structures and figure out what is the difference between them. All right, so 1,2 addition, our 1,2 addition product is this one here. And 1,4 addition is this one here. Okay, there we go. And so the difference between these is basically where the double bond is, right? Our double bond, we have a secondary bromide versus a primary bromide. Our double bond has basically one carbon attached to it. So if we look at all the stuff that's connected to this double bond, we got 3 hydrogens connected to that double bond and only 1 carbon. Whereas over here, we have 2 carbons connected to it. Right, so 2 hydrogens and 2 carbons. So we categorize double bonds by how many carbons they are attached to, right? Just like we do with carbocations, just like we do with alcohols or bromides or anything, right? We look at the carbon that's there and say, how many carbons is it attached to? So an alkene with one carbon attached, one carbon attached, we call this monosubstituted, right? It has only a single carbon group attached to it. These are the least stable alkenes. Um, alkenes with two carbons attached are disubstituted. And so on and so forth, right? We have tri-substituted, which of course is 3 substituted, and then we have tetrasubstituted, which is 4. Tetrasubstituted double bonds are the most stable alkenes. They're the least reactive, etc., etc. So this is 3 carbons attached. This is 4 carbons attached. So we look at these two. This one, the 1,2 addition product in this case is monosubstituted. This one is disubstituted. We look at the pattern that I just wrote out. Disubstituted is more stable than monosubstituted. In this case, this is the more stable product. Okay, so that makes sense, right? That's easy enough. We look at the alkene, we figure out how many carbons are attached to it. That's our more stable product. It would make sense that that would be the favored product, the product that we're likely to get out, right? It's not that simple, right? There are other things we have to think about. Let's look at this a slightly different way. Yeah, maybe. There we go. Let's look at the cations, the resonance structures, right? So when we did 1,2 addition, right, we went through a cation that looked like this. Secondary cation. When we did 1,4 addition, we went through a cation that looks like this. Right? After moving that pi bond over, we have a primary cation. All right. So we know our carbocations. Which one of these is going to be the more likely one to form? Right? The more substituted carbocation is going to be more likely to form. And so the secondary cation is going to be more stable. And thus we would predict, if we look at the carbocation stability, that 1,2 addition would be the favored outcome of this reaction. So of course now we've argued it both ways. If we look at the products, right, the 1,4 addition is favored in this case. If we look at the products and we favor the most stable product, we get one thing. If we look at the intermediate, the carbocation, and we favor the most stable intermediate, we get a different thing. And so how are we going to make sense of this? And so we need to kind of have a way to represent this. And so we're going to use a reaction coordinate diagram to show kind of where these stabilities are, and then think about how can we manipulate this reaction to favor the more stable product, or how can we manipulate it to favor the more stable intermediate.